let me begin by reviewing from last time, and you will see that there are some revised notes which are available to you. And I'm going to stay in this combinatorial domain today as well. And then when we come back on the 8th, we will go back to Khovanov homology and Lie homology in relation to these things. So I just want to quickly go back over the notes from last time and point out some examples that are here. So we talked about the binary bracket, and the binary bracket is related to doing two colorings of the virtual diagram and then examining the smoothings that result. And as we have said before, these can correspond to cycles in Lie homology, which is one reason why we're thinking about it, but it's also interesting for its own sake. So the binary bracket has this expansion where this means that these are colored differently with two colors. And then you see that if you were looking at a single loop, then it would be possibly red or possibly green, each one evaluating to 1, giving you the 2. And then in general, you look at all the different colorings of the knot or link and take products of A's and A inverses accordingly. And if you have a classical one component knot, then there are two colorings exactly, and each one of them is going to give you A to the writhe of K. And the reason that you get the writhe, and notice that it's working, just take a look at, say, the Trefoil example. I do an alternate coloring in red and green of the Trefoil knot and look at the smoothing types, and they're all in accord with the Seifert smoothing. And we have discussed this before, that the Seifert smoothing will correspond in the case of classical knots. And so you get A smoothings in each case, and so you get A to the writhe of K. And then, since there are two of them, this bracket will give you 2 times A to the writhe of K. And of course, that means that once you've normalized it, it doesn't give you any information for classical knots. But if you have a 2-component classical link, then you'll get some linking numbers out of this, and still not a huge amount of information. But if you have a virtual knot, then you find that when you do this alternate coloring, then you find smoothings which are at variance to the Seifert smoothings. Now, this is really quite interesting because you'll recall that when we normalized our Khovanov homology for virtuals, then the cut point in additions made the two colorings work out and give you Seifert smoothings. But without those cut points, then you pick up information which is strictly about the virtual knot. And let's see how it plays out in this invariant. So here the writhe is 2, but the bracket is 2 times A to the minus 2 because these smoothings are in the opposite direction. We'll look at this more closely in a moment. And then, well, this is something we did last time. We looked at the invariance under the second Randomizer move and went through it. I won't do that again. We looked at the behavior under the first Randomizer move, which is quite simple. It either multiplies by A or A inverse according to whether the curl is a plus curl or a minus curl. And I will define the normalized one, let's call it B for binary bracket of K, BK, to be A to the minus the writhe of K times the bracket, just like we usually do, but A to the minus writhe because it goes A inverse under the curls. And this will be invariant under all 3 Randomizer moves. So you see that we can check what happens if we have a 1-component virtual. And I think I explained this formula a little better in another slide, so I won't bother you with it right now. But then there's the invariance under the third Randomizer move, which I didn't bother to point out to you carefully. And let's look at it now. because you can do an amusing exercise for yourself, checking the other cases. You see, all you have to do is write down a sample diagram and then look at the corresponding flat diagram at its colorings. And there are many cases, because here I'm assuming that it goes in red here, goes in red here, and it goes in red here. But it could have gone in red here, green there, and so on, all those different ones. But choose one and look at the before and after shots, look at the smoothings, and you will see that you get the same collection of coefficients. This is a B smoothing right there. This one is an A smoothing, and this one is an A smoothing, and you get an A smoothing, an A smoothing, and a B smoothing afterwards. So the third Randomizer move leaves its invariant under the third Randomizer move. And now here's an example that we did last time, but I've been a little more careful in drawing it. I have this link, and I decided to orient it the way I've oriented it with the red arrows. So it has one positive crossing and two negative crossings. And then here are the states of this link. Well, half of the states of this link. I took this component and I started it on red here and started the other component on red here. Then I took the same starting on red here in the rather circular looking component and started it on green in the other one. And now you see that what happened is that this smoothing remains the same, but the other two flip between these two. And we'll get two versions of this and two versions of that. So we're going to get that the bracket of it is 2 times a cubed plus a to the minus 1. And then, since we're interested in writing down a fully normalized invariant, we'll take the above orientation so that the ride of this is minus 1. So we're going to have a to the minus ride, which is an a, multiplied by the value of the bracket, and we get 2a to the fourth plus 1. And that tells us a couple of things. It tells us that this link is this virtual link is inequivalent to its mirror image, because just as with the usual bracket, if you flip all the crossings, you'll change all the signs of the A's. The A's will become A inverses. And it's non-trivial. It's a virtual link. So that's how it looks for links. And it may be that we could characterize exactly what the combinatorics of the exponents are. But as you see, with multi-component links, it depends on the orientation direction of the coloring, what contribution you get. So it is what it is, and it's an interesting invariant to think about. Now, on the other hand, if you are dealing with a crossing and you ask, is it going to give me an A or an A inverse when you use the binary bracket? Then again, I'm just repeating what we said last time. Here's this crossing, and we take a walk on the diagram until we return to the original crossing. And in the diagram, every motion through that loop goes through twice, but some of the lines that go through may go through an odd number of times because of virtual crossings. And then this would be an odd crossing. So an odd crossing is one where there are an odd number of virtuals that are intermediate in here, or another way of saying it, there are an odd number of classical meets as you go from here to here. And if you have an odd crossing, then you will get a flip away from the Seifert smoothing. And if you have an even crossing, you will get the Seifert smoothing. So we know in terms of this parity when we get the Seifert smoothing and when we don't. And so I will define epsilon of a crossing to be +1 when it looks like this and -1 when it looks like this. And these are the standard crossing signs. And then you see that a to the minus ride of k is the product over all crossings of a to the minus epsilon of that crossing. On the other hand, the bracket of k is equal to twice the product over the, this is for one state evaluation, product over the crossings, over the even crossings of a to the epsilon of c, that's the sign that you would get from the Seifert smoothing, and the product over the odd crossings of a to the minus epsilon of c because it flips on an odd crossing. So when we normalize it, we're multiplying by the product over all the crossings of a to the minus epsilon of c times this, which means that the even crossing part is canceled out and the odd crossing part appears twice. And so we get, this is for one component, we get twice the product over the odd crossings of a to the minus 2 epsilon c. In other words, we get the a to minus 2 times the sum over epsilon of c for the odd crossings. But the sum of the signs of the odd crossings is what we have previously called the odd rive. So you see that bk is equal to 2 times a to the minus 2 times j of k, where j of k is the odd rive of k. And in my personal history, that's how I discovered the odd rive. You can imagine somebody discovering the odd rive quite naturally without having to go through seeing it inside of some other invariant. But, you know, it's chancy how you discover anything at all. And this happens to be the way I discovered the odd rive. So it's amusing to look at it, look back at it that way. So indeed, the invariant bk is quite non-trivial when you have a virtual knot, the odd rive being an interesting and very simple invariant of a single component virtual knot. And we've seen other things in earlier lectures about the odd rive, such as its invariance under concordance of knots and things like that. Now, what about more colors? And that was another thing that we talked about last time. What about more colors? What happens if I were to expand this but used more colors? Well, the answer is it ends up being then yet more closely related to coloring problems for graphs, and we're going to talk about that. And on the other hand, it won't be so easily topologically invariant if we start expanding it on more colors. So you might manage to expand it on more colors and get topological invariance, but it would involve other rules. So for example, one can get expansions for the Helmholtz polynomial using many colors having to do with the group SLN, but that's another story. In here, in this very simple bracket state expansion structure, putting in more colors tends to destroy the topological invariance. But I am interested in 3 colors. And it turns out that the 2 colors and the 3 colors are very closely related. And we began to talk about this as well last time. And I thought this time I would go over these notes and then amplify a number of points. So a famous problem is the 4-color theorem, which can be reformulated as try to color trivalent graphs in the plane with 3 colors on their edges so that 3 distinct colors occur at every vertex. So I have produced such a coloring for this trivalent graph. You see, I have green, blue, red here, and I have green, blue, red here. And I have green, red, blue here. There are 2 possible cyclic orders, and this has been colored. And it turns out that the 4-color theorem is related to that. And it's worth understanding how the 4-color theorem is related to this in case you haven't seen this before. So this slide is showing you that. What I do is I take the 4 colors to denote the Klein 4 group. In other words, the direct sum of the group Z2 with itself, or the direct product of Z2 with itself. And that has 4 elements in it, that group. and the square of, and I call them white, red, green, and blue, and white is the identity element. And the square of each color element is the identity element, and the product of any two colors is equal to the third color. The three colors correspond to the edge colorings of the graph, but we use the fourth color for regions, and then the relationship between them is illustrated here. When you have a coloring on a region and another color on an edge, multiply them together to get a color on the next region over. So in this case, I have a white on the outside and I multiply by red and I get red. And then I multiply red by green and I get blue. And I multiply blue by green and I get red. And I multiply red by red and I get white. And I multiply white by green and I get green. And I have a four coloring of the map, which is derived from the three coloring of the edges. This works both ways. If you had a four coloring of the edges, if you had a four coloring of the regions, well, then you could choose a coloring of the edges in relation to that by doing the same process in the other direction. So this is the sketch of how four coloring is related to three coloring. And the three coloring problem is very interesting and nice because you see the three colored gadgets don't have to be planar. It's interesting to look for uncolorables, but there aren't any in the plane because of the four color theorem. But on the other hand, if you get outside the plane, you can find them, and they're very interesting, and they reflect on what's going on in the plane. So that's the four color situation. Now, another thing about a coloring, this is the same coloring that I had here, is that you could choose one of the colors and mark those edges. That's what I've done. I marked the green edges. And the result of marking the green edges is that I get a collection of edges that take all the nodes in the graph, and a collection of edges that are disjoint that take all the nodes in the graph is called the perfect matching. And so the coloring, having a coloring in three colors, is related to finding a perfect matching for the trivalent graph. But it's a very special perfect matching. It's an even perfect matching. And by even, I mean that if you were to remove these edges, the ones that have been circled in blue, then the circuits that are making up the remaining part of the graph will be even. For the circuit I'm thinking of is red to blue to red to blue to red to blue to red and back to blue. So there's only one circuit here, but there are an even number of edges in that circuit. And of course there are, you know that because it goes alternately red and blue. And every circuit in the complement of the matching edges will alternately be colored in two colors, red and blue, you see? So these are two color alternations as long as you choose all these edges for the perfect matching. So you need an even perfect matching, and then you've got the coloring, and vice versa. Because you see, if you chose an even perfect matching somehow by hook or by crook, then you could color all of them green, and then you could alternately color in red and blue the even cycles in the complement of them, and that would give you a three coloring of the graph. So the four color theorem actually says that every one connected, every graph without an isthmus trivalent in the plane has an even perfect matching. That's another way of thinking of the theorem. So graphs with perfect matchings are interesting to think about, and we'll be coming back to that. And then we talked about the Penrose formula. And Penrose had this brilliant formula. And I put into the Dropbox a copy of Penrose's very interesting paper called Applications of Negative Dimensional Tensors, in which he explains this formula and other combinatorial formulas related to graphs. You'll find it there. Penrose formula says you can remove an edge, any edge, no perfect matching required here, smooth it or put a crossing in it, and subtract, and evaluate the loop to be 3. This is for 3 coloring. And this will give you the number, the exact number of different 3 colorings of your trivalent plane graph. And it has the curious technical feature of only working for plane embeddings. If you take non-planar graphs and try this out, it can give you the wrong answer. But here's an example of it working. You take this theta, I turned it vertically and used the formula, and I get 6. Or I can take this dumbbell, which doesn't have any colorings, and use the formula, and it gives me 3 minus 3 is 0, because loops that have a virtual crossing in them are evaluated the same as loops, or just loops, 3. And G doesn't always work when it's not planar. And an example of that is this gas, electricity, water problem graph, which you can try out. So I gave you this as an exercise. You can find that it has 12 colorings, and it's detecting none of them when you use Penrose. And then we talked about the tautological coloring formula. And the tautological coloring formula just says that if you're going to color this graph, it could either be colored in such a way that these 2 edges have the same color, these 2 edges have the same color, and they're different. Or these 2 edges cross over so that this has the same color as that, and this has the same color as that, and they're different. And this is a tautology. This is just expressing what it means to be colorable, because you see, it might look like this: red, green, blue, and red, blue, green, opposite cyclic orders, in which case the reds are on the left and the greens are on the right, and you can pull them apart and just say this. And if you want to reconstruct the coloring, you press it together and put in the blue. Or it might be the other way around: red, green, blue, red, green, blue, same cyclic order, top and bottom, and then these colors are on opposite sides, and you have a crossover line, and again, the instruction that it's different. And now there's a very interesting thing about the tautological expansion. I'm showing it to you here as an algorithm. Suppose that I wish to use it to find the colorings of a graph. So I put down this graph, and I choose a perfect matching for it. Remember, finding a perfect matching is easier. You can fairly easily find a perfect matching. If you want to find an even one, that may be a little harder. And it's the even one that gives you the coloring, but just get a perfect matching. So I've chosen one. And then I can take each one of these and do the simple smoothing state, and I will get a collection of loops in the plane with instructions between the loops that says, thou shalt not be colored the same. And it may be uncolorable, like this one is, you see, not colorable. You can't color something different from itself. And here there are 2 self interactions and some other interactions. Well, what does the 4-color theorem say in these terms? It says something interesting that should kind of raise your eyebrows as a knot theorist, because it feels very much like you're looking at some subtle structure of states of the bracket, only it isn't necessarily reflecting on the bracket. We don't know exactly how it is. But what does it say? It says that this might not be colorable, but some replacement of standard smoothings by crossover smoothings will make it colorable. So that's what the 4-color theorem says in state loop form. You put down a bunch of disjoint Jordan curves in the plane. You put some conditions between them that say thou shalt be colored differently, and then it might well be uncolorable, but according to the for color theorem, if you switch some of these sites, where this is what I mean by switch, replace the smoothing by the crossover, then it will become colorable for at least one choice of such switches. That's what the four-color theorem says. So in our example, here's our example. I wanted to get rid of this self-crossing and I wanted to get rid of that self-crossing. So I tried putting switches there and there. And now you see the loop configuration changes. I have this loop and this loop, that one and that one. And indeed, I can color this one red, that one green, this one blue, and that one green. And all conditions are met. And it gives me a coloring. And since that's colorable, I can go back to my graph or my original graph, and I have a coloring of the original graph by squeezing it together at the smoothings. So I find this version of the four-color theorem very tantalizing because it is indeed some kind of subtle property of the state structures that we're already thinking about in the knot theory. And of course, you can find the even perfect matching as a result of having found the coloring. And the perfect matching that I've drawn here is one. It's an even perfect matching. It's different from the original perfect matching that I started with. I would like to show you another example of this, as a matter of fact. As long as we're talking about this, let me digress into today's lecture and show you a little more about this situation. So you understand we're in a digression about the relationship between graph theory and virtual knot theory, and there will be quite a bit more, as you'll see as we go along. It's a very rich kind of connection, as you'll see, I believe. So here we are, lecture 11. Let's see, let me begin by showing you an uncolorable. An uncolorable graph. By the way, uncolorable trivalent graphs are called usually non-planar. Are called snarks. And this terminology is due to a famous graph theorist named Blanche Descartes. Who is sometimes known as William Tutt. William Tutt's true name is Blanche Descartes. Perhaps you didn't know that. Or perhaps it's the other way around, that Blanche Descartes' true name is William Tutt. And the terminology comes from a long poem by Lewis Carroll entitled The Hunting of the Snark. So I wonder, perhaps you'll tell me in discussion later when we stop, how many of you knew about this? It's fun. Sometimes William Tutt, who is a very, very famous graph theorist, of course, um, would write under the pseudonym of Blanche Descartes. So this is the uncolorable, the most famous uncolorable in all the world. We'll denote this graph by P. It's called the Peterson graph. And there does not exist an edge free coloring of P. We should prove this. Of course, one way to prove this is to simply try to color it and find out that you are foiled in every case, but that's a long enumeration. And sometimes doing a long enumeration is exactly what will give you an intuition. So I wouldn't say don't do that, but I'm going to give you a more simplified mathematical argument rather than try to enumerate its colorings. It's non-planar, of course. And this is not its minimal crossing number. This is just its most well-known diagram. So as you see, it has to do with 5. It has to do with taking a cycle of order 5 and another cycle of order 5 and connecting them together by some perspicuous permutation. And the Peterson graph, for one reason or another, it ends up being an example that comes up in lots of different graph theory problems. I won't try to enumerate them, but I do recommend that you look at a book called, see the book entitled The Peterson Graph, an entire book of about 300 pages devoted to the Peterson graph and its properties. Okay, now what I'm going to do is rework this a little bit, the graph, I mean, so that I can play with it a little more easily. So just one moment. Let's just call it lecture 1 for now. Yeah. So here's Peterson again. I'm going to draw it in a different way. So I claim that this is graph isomorphic to this beast. You understand that crossings, I'm working with graphs, so I use a graph theorist convention of not putting circles around my virtual crossings unless I really need to, but those are virtual crossings. And this actually is a minimal um, crossing representation of Peterson. You won't be able to draw it with fewer than two crossings in the plane. You might try to prove that, but you might also try to prove, all right, exercise. To make an isomorphism from this to this. Not hard. You'll find it's not hard. But now the Peterson looks a bit like Mobius strip. And now I'm going to apply the tautological identity to it. Gonna run out of space on it. Let's see. Oh well, no, I can apply the tautological identity by saying goes to here plus, and then we will put in what we have to. So we would smooth it this way, or cross it over, right? All right. Tautology. To remind you, if you look at the notes again, so this means that a coloring of this must be either a coloring of this or a coloring of this, with this stipulation that this, whatever color this gets a different color. Whatever color this gets a different color. But now, if you were to look at these carefully, let me give myself enough room to do it on one slide. Let's not do that. Sorry, I'm just trying to get a little more room here. Give you time to think. Okay. So by tautology, we go here. And now I want to simplify this, that's all. So you see, having a crossover doesn't mean anything at all as far as our coloring combinatorics is concerned. So this is just saying that this loop here is, this loop here, this edge here, has to be colored differently from this edge here. And over here, we can simplify that by doing a flat Randomizer 2 pull apart. And these have to be colored differently. But it's quite symmetrical. You see, this is the same condition. These both the same condition. That has to do with the symmetry of my situation, right? This is perfectly symmetrical, And here you closed it at this end, and these loops have to be colored differently. Here you closed it at this end, and these loops have to be colored differently. So there's only one condition. And so, then we have reduced the problem to asking whether does there exist a coloring of this graph with these colored differently, and that we can investigate by hand. Let's do it. So now I'm facing a little problem. It looks like this. And now the question is, exists different? Same? And we're going to find out answer, forced, same. And that implies Peterson is uncolorable. Easy to forget what we were just doing, but remember, we found out that in order for Peterson to be colorable, there had to be a coloring of this so that these were colored differently so they could be pressed together in the right way to give a coloring for Peterson. And now you can just try it out. Basically, let's just try it out and see how things look. Red, blue, green. All right. If this is green and that's red, this has to be blue. Green and blue make red, and that transmits all the way over to there. Red and blue make green. Blue up here and green down here make this line red. Blue and red make green. Green and red make blue. Blue and red make green, and red and green make blue. And that means that green and blue make red. And you see, this was forced. I just did a forced series of, once I made a 3-color choice, then I had a forced series of moves from left to right. And so these are forced equal. And I think you'll agree that that's a better method than looking at all the colorings. And also notice that if we had a black box, with an edge sticking out of it and a little crossover put in for good measure, right? And this is a black box sum graph. And suppose this is, let's say, suppose that this is a critical uncolorable, by which I mean any smaller is colorable, right? Then the same argument shows that, let's put an arrow here so that there's some asymmetry in our black box, shows that both force same. It might no longer be symmetrical like Peterson, but if it's going to be uncolorable, then you can't have a coloring where this is different from that. And if it's critical, these will be colorable. And so that's how, that is the form of a smallest counterexample to coloring. You have to have a black box which transmits the condition from left to right of uncolorability and transmits it vertically as well of sameness, excuse me. Sameness gets transmitted both horizontally and vertically. And that's what happens in Peterson. And this is one of the things that leaves you somewhat convinced of the four-color theorem, if you think about it, because it's very, very difficult to imagine constructing an example of this kind that isn't planar. You see that what happened in Peterson was that there was this triple line going this way, which enabled the transmission of forced sameness this way. And there was a triple line going this way, which managed the transmission of sameness here. And those two managed to get superimposed on one another in an appropriate way. Now, I'm not saying anything that makes rigorous mathematical sense. I'm talking about the realm of designing examples. You go ahead and try to design a critical uncolorable, given that you know that these are the conditions that it has to meet. And you will find that you would easily reinvent the Peterson. You will reinvent some variants of Peterson, but you're going to be off the plane in an essential way. Now, as long as I said all that, I better say a little more. Note the following. I put into my black box a crossover. That's my black box. So I'm going to make this is a non-planar black box, of course, but you're going to see it has some interesting behavior, right? If I connect it this way, it forces same. And if I connect it this way, this force is the same. So this is the most elementary forcing box. And what if we use it to construct an uncolorable? We can. It's a forcing box. And this is what we connected up to make the uncolorable. And this is an uncolorable. But in fact, planar with isomers. Right, this is graph isomorphic to the dumbbell. So this illustrates the logic of the situation. If you try for the simplest possible thing, you can, in fact, by the time you reconnect the whole thing up, get a planar example, and that's your last planar example you're ever going to get, the graph with isomers. And you can see Peterson as a kind of an extra decoration on this graph. So good luck if you're interested in proving the four-color theorem. It has a tendency to make itself look obvious and then pull away when you actually try to write down a rigorous proof. Yeah, I was making these remarks and I wanted to go a little farther on this line. I hope you don't mind. I like this topic. There's another paper, I'm going to put it in the Dropbox for you, by Rufus Isaacs. A paper in the American Mathematical Monthly. Oh, a long time ago. I've forgotten now. I'll put it in the Dropbox. Many years ago. And he showed how to construct infinitely many non-planar snarks. And his gadget, this is the Rufus Isaacs gadget. This is a little box with 3 inputs and 3 outputs. And he called it J. And if you take a J and another J and another and another and connect them all up, and feed the end into the beginning, and you take 2n plus 1 of these, so we'll call this thing J2n plus 1, odd number. This is uncolorable. For you, with no extra charge, another exercise. This is a delightful exercise. Easier than my previous proof that Peterson is uncolorable. You think of this as a little transmission box and examine what can go through, and see that the only significant ones are when there are 3 different colors. And then you see that when there are 3 different colors, they will get permuted and they will undergo an odd permutation. So there's no way to get back to the identity if you go through an odd number of odd permutations. So it becomes uncolorable. Isn't that great? And it's really a nice exercise. You'll be convinced if you stare into that. That little gadget, of course, that extra crossover is making things non-planar. You won't get anything planar out of this. But this was a very nice breakthrough at the time. I don't know how it ended up in the monthly, but I'm glad it did, because it then got written in a very nice expository way. You'll see when you look at the paper. As long as we're chatting about this, you should see J3. Huh. Might as well. That's J3. And you might wonder, how might that be related to Peterson, since it's very similar in size? It's a little larger. So another exercise for you. Collapse this loop to one node and get Peterson. I kid you not, right? There's another picture of Peterson. Just these collapse to one node. Then you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 nodes, just like Peterson. It is Peterson. And that's an example of Tuck conjectured and Robertson, Seymour, and Thomas proved that every non-planar, uncolorable has a Peterson minor. On a graph, minor means that you can obtain it by deleting edges or contracting edges. So contracting that loop to a point is showing that this has a Peterson minor. And then you can have some fun looking for the Peterson minors in the J2n+1s, if you like, right? Now, one more exercise about coloring that I think is quite interesting, and then we'll get back to the direction that takes us back to knot theory. Right. Here's a little coloring problem written in circle form. All right. So this is for circles mutually touching. This is not colorable. Four-color theorem implies that there exists some switching of the kind, replace this by this, to get a three-colorable state. Okay, exercise. Find that switching. Find all such. Right? Right? There's at least one. Find them all. You have here 1, 2, 3, 4, 5, 6. So that's only 64 things to look at. Nice exercise. Okay? There's your exercise. Now, Now we're going to head back in the direction of knob theory. Penrose formula looks like this. Right? With a loop value of 3. Now, we know all about Skane polynomials and things like that. So it's natural to ask, what about a Penrose polynomial? That is, what about setting the value of the loop equal to a delta, let's say, some delta, and try to do the calculation again and get a state sum involving delta? We could put coefficients in, so on. But let's leave it just the way it is with the minus sign and the plus sign and see what would happen. So we better just try some examples and see what would happen. Let's try this one. And if we choose a perfect matching, then we have a specific algorithm for computing it, right? So we could choose this perfect matching and try it out. And then let's see what happens. This will go to and then there'll be a crossover. So then there'll be minus. Be like that. And then maybe we should work out what happens if there's a little just a little aid to calculation. If you were looking at this somewhere in a graph and doing the Penrose calculation, then this is going to be equal to, we'll use this one. So this will be equal to this minus the crossover one. And that's going to be equal to delta times this minus this, which is delta minus 1 times this. In the case of 3, it would be 2. In the case of delta, it would be delta minus 1. So this is a little bubble of that kind. And so this is going to be equal to delta minus 1 times the value of the loop, which is delta. And this one, I think I have to expand it. And then I would get crossover and one of these minus crossover, crossover, like that. And so according to that, I get delta minus 1 delta minus delta squared, which is delta times 1 minus delta. So I get delta minus 1 delta minus delta times 1 minus delta, which is delta minus 1 times delta. So I get 2 times delta minus 1 times delta. All right. So I can calculate a Penrose polynomial for a perfect matching that I've chosen. Now, maybe I have room here to do a different perfect matching. Let's try it. Same graph. Let's try this perfect matching. Well, that's a bubble. So the bubble goes away, and I get multiplied by delta minus 1. And then there's another bubble. So this is equal to delta times delta minus 1 quantity squared. Well, these are not equal. What happens at 3, just to check? At delta equals 3, I get 3 times 2 squared. And at delta equals 3, I get 2 times 2 times 3, which is 12, which is 12. So we're okay at delta equals 3, but in general, not the same. So this Penrose poly depends on the perfect matching. So Scott Baldridge said, and some of this work is joint with Scott I'm talking about here. Scott said, we have a perfect matching polynomial. Okay, so that's one way to think of what happened here. And I did this little mathematical experiment for you. The Penrose polynomial Penrose formula is defined independent of perfect matching choice. In fact, it would be fun to tell you, but I don't want to do it right now, how to prove the Penrose formula is true. And then you would see it didn't depend on any perfect matching choice. But as soon as we decide to deform the Penrose polynomial into a polynomial rather than an evaluation, then it depends on a choice of perfect matching. Any choice of perfect matching gives us an algorithm for computing it. So that means that if we defined the Penrose polynomial this way, it would distinguish this perfect matching from that one. There is no graph isomorphism which carries these perfect matching edges to those. In this case, of course, that's not hard to tell just by looking. But in general, that's a nice combinatorial question. Is this perfect matching isomorphic to that one? And here we have a polynomial that can discriminate. Now, Scott got interested in this phenomenon, and he had the idea that things looked analogous to Khovanov homology. And so he defined a graph Khovanov homology that would correspond to some of these perfect matching polynomials. And that's where I got into the act in this case. Because I looked at his perfect matching polynomial, and let's write it down again. The perfect matching polynomial that we might generalize in this way, just to, if we were looking for analogies to Khovanov homology, we might try something like, well, let's see, what about that? Minus Q times this. What was it that we were doing here? We had a crossover. And we could have the value of the loop be equal to Q plus Q inverse, which looks rather analogous to our way of dealing with grading in Khovanov homology. So then that's what he did. And he then defined graph polynomial and a graph Khovanov homology. And it all works out all right, and you can define everything. And I'm looking at this and thinking along the lines of my old paper on self-linking number, and let's make a definition which corresponds to my thought. I'm going to define K, which takes graphs meaning trivalent with perfect matching. And we called these graphemes. Okay. Graphs that are trivalent with a given perfect matching. The virtual knot diagrams. Virtual link diagrams. By the following stratagem, that the perfect matching edge will be sent over to a crossing combined with a virtual crossing. Or another way of putting it is that a virtual edge with a virtual crossing over on the right will be sent to ordinary crossing, because virtual crossings are idempotent after all. So what happens if you do that? Well, let's draw the pictures and see. One way to draw the pictures would be to erase this part of the board, although it's a little quick to erase, but we're going to put it back in a moment anyway. And then let's write under here what this would go to, or let me see. First of all, that's a virtual crossing. Right now, I'm going to draw virtual crossings in my graph category so that you can see where they happen. And we want to see from this what would happen to the thing that goes to a crossing. And the thing that goes to a crossing is this combined with this, right? So we can just add that in. And then we would have that this would be equal to that minus Q times that and that's equal to this minus Q times this, right? And this is supposed to be correspondent via the K-map to the crossing. And you notice I have the A crossing vertical here. So this is the bracket, right? And of course, we're taking the value of the loop still to be equal to Q plus Q inverse. So you see that the perfect matching polynomial goes by way of the K correspondence to the bracket. So we have a different one other than the usual correspondence between bracket and graph theory. We have that this generalization of Penrose to a perfect to a perfect matching polynomial corresponds to the bracket. And And then the matter of doing Khovanov homology is conceptually much more clear now. We can we can say, okay, I know how to do Khovanov homology over here, and I will pull it back to the techniques of doing Khovanov homology for these graphs and rewrite and try to investigate how Khovanov homology for these graphs will inform us about various things. So this is the graphenes to virtual knots program, and the way this works is maybe it's a good idea to just show you some slides about this that are already prepared to give you a little tour right now. So let me do that. Let me drop this. And we took a long digression, but I wanted to show you that kind of correspondence. In my notes from lecture 10, I gave you another exercise about looking at perfect matchings for this, and a few more things of that ilk. And then I started talking about the K-map in those notes a little bit, and a little bit about Penrose. So we've gone into this in much more detail. But now for a little more about this right now, let me show you some notes about this that you could look at, because I'll put these into the Dropbox. So you have a couple of weeks, you might want to look at some of these things I'm telling you about. So one thing is, here is a little description about the four-coloring and some other things that I haven't told you about four-coloring that I won't tell you now, and about the Penrose formula and how it works and how to prove it. And then there's the matter of virtuality for graphs. When I speak about graphs, I can have virtual crossings in the graphs, but I don't have Randomizer moves necessarily. And I may want to create new moves on the graphs that could correspond to Randomizer moves. But I will always have the detour move, you see, because the detour move is always what we want when we have virtual crossings. We have an immersion of a graph in the plane, and we want to be able to cut out a consecutive sequence of virtual crossings and put it somewhere else. That just allows us to move the graph around and get different graph embeddings, immersions. All right. And then here is the story about the three-variable perfect matching polynomial that I was just telling you about, and the K-map and how that works, and how we go back and forth. And some remarks which we can skip in the last 5 minutes about orientation. If I'm not going to be really careful about orientation, then I'm going to need to take things up to the Z move, up to flanking by virtual crossings, and work on virtual knot theory modulo Z equivalents to get these correspondences to work. But we can also be more careful about orientation, and then we will be mapping back and forth to regular virtual knot theory. There's a little bit of a remark there. And then this is the correspondence to the bracket. And then you can look at the Randomizer moves, of course. That's the next part of this project. You see, you say, all right, I have a Randomizer move in knot theory. What does it correspond to over in graphene? And you just go ahead and do the job. You see, if you had a little crossing there, it gets mapped to a perfect matching edge and a vertex. And so you get Randomizer 2 move that looks like this. You don't need to see the detail. Or Randomizer 3 move that looks like this. And then what we're saying, though, is that with this, with defining the polynomials with their topological parameters and pulling them back to the graph theory, then these polynomials are perfect matching polynomials, but they are invariant under certain changes from one perfect matching to another. the crossing in the knot theory is replaced by the perfect matching edge in the graph theory. And you will notice that in this correspondence, something which you can be very curious about is coming about, namely that if you just took a bare graph, there would be many perfect matchings on it. Each one of those perfect matchings maps over to a certain virtual link. So if you draw a trivalent graph, it corresponds to a family of virtual links that are obtained from the perfect matchings that you can draw upon it. What is the meaning of those families? We don't know yet, not really. Then certain evaluations are very interesting, like evaluating A at I, or the Jones polynomial at 1. And I won't bother you with that, but you'll see in these notes that I'm giving you. And then, of course, you can calculate examples. Like here we have the mirror image, what I called the mirror image of the standard virtual trefoil. And it goes over to this graph. And here's the virtual trefoil, and it goes over to a slightly different graph. And then you can calculate the polynomials and find out that indeed these two graphs are different. So one's intuition about knots may be stronger for having worked with knots a long time, but you can begin to develop some intuition about when graphs with perfect matchings are going to be equivalent under these circumstances, and that's another question. So there are many questions here. Let's see, that needs to be turned. So there. Another amusing one. Here's the classical trefoil knot. And I put it in braid form and shifted it over by the K inverse map. You see, became a perfect matching edge and a crossing and so on. And then you look at this graph and you find out it's good old K33, the gas, electricity, water problem graph with a certain perfect matching on it. The correspondences are interesting to think about. And then this goes back to our coloring theme, but I think we're going to quit in a minute, but I'll show you a couple of things anyway. Our coloring theme, remember the question was, does it have an even perfect matching, right? Well, if you have a classical knot or link diagram and you take the corresponding perfect matching graph, then it's even. And hence the graph is three colorable, but it might not be planar because it's picking up virtual crossings. I'm just telling you some results without reciting proofs, because you can have fun looking at the notes anyway. If you have any virtual knot diagram and you let script G be the inverse K-map applied to it, then it's three colorable trivalent graph, any virtual knot diagram. Knot diagram, but not link diagram. Link diagrams can be not three colorable. And other things. These is a little course of notes here. And then in these notes, I go back and work with the tautology again and some examples. Even one of your exercises is in here. We better go back past that quickly. And so it goes. And as you see, the theme here is that we have this conduit that goes back and forth between virtual knots and graphs, and we can do Khovanov homology and other invariants over on the graphs, either by direct definition or by pulling back a definition that exists in the topological case, and it gives us an arena in which we can ask a lot of questions. Some of the questions we're asking are graph theoretic about certain kinds of embeddings of graphs. Others are not theoretic. And we hope that by working in this, which we are working at the present time, we'll be able to get more insight into both subjects. Let me finish with one more example that I was doing the other day just for fun, so you see it. I have to find it. Perfect matching talk. Wait. Peterson. There. All right. Here. I don't know why that's obscuring. Just a moment. Oh, I understand. Let's get rid of that. Okay, there we go. Here is Peterson in a slightly different form. It's the same as I was doing before, connecting up perfect matching edge and crossover with the fourfold. And then I chose a perfect matching, and then I made it into a link by mapping it over into a link in this form. And I find this link. And then I'm curious what I can see about this link. So this is just the kind of thing that you might do in this back and forth. So I have this link, and I would like to know something about it. So then I code it up and figure out its arrow polynomial. Do you remember the arrow polynomial from long ago? The arrow polynomial looks like this, and we can translate it into the graphs if you like. The arrow polynomial looks like the upper part here, crossing, goes to A times crossing and B times a special cusped smoothing. And then that can be translated, and this is something we hadn't translated before at all, so I'm thinking about it like yesterday. What happens if you translate into graphemes the arrow polynomial? And in particular, what happens to the example that I was just looking at? So I calculated its arrow polynomial, and I found out that it has a variable that tells me that it can't have less than 3 virtual crossings. Now, the example that we were looking at is this one, and it has 4 virtual crossings. It can't have less than 3, and I don't offhand see how to get it to have. I don't see how to prove that it has 4 or to remove 1. I'm not doing it up to Z equivalence here. I'm just doing it. Up to Z equivalence, we could probably simplify it considerably. But this back and forth leads to lots of examples that you might start to think about like that. So that's a good place to stop. And I will share those references with you, and we will be heading back in the direction of the Khovanov homologies when we meet again on the 8th.
Thank you very much. Very nice talk.
Questions?
So you discussed the class of trivalent graphs.
Yeah.
And what about another valensity? Is there some similar?
What about what identity?
About 4 and more. If you have more than 3 valent vertices.
Different valence? Is that what you're asking?
Different valence, yes.
Yeah. Well, I don't actually know exactly what's going to happen with different valence. The trivalent problem is very strong for the coloring problem, as you know. And if you have If you have a graph with higher valence vertices, then for coloring problem, if it was a map, you blow up the vertex. You cut the vertex, you cut the node out and put a little circle in, and you get a trivalent graph.
Yes.
So so my first reaction to dealing with higher valence graphs is to do that. On the other hand, when we're dealing with graph embeddings rather than this subject, then it's natural enough to ask for higher order valence graphs and think about how they would move around, what identities you want for them.
Okay.
So, but this mapping between a non-theoretic crossing and the trivalent vertices is very natural, and I don't know how to shift it to a higher valence vertex. There might be a possibility.
Okay, yeah. Thank you.
Mm-hmm. Any other? Okay, have a great holiday, and I'm looking forward to seeing you in a couple of weeks.